So this section 6.3 is about the sampling distributions and the estimators, which means we will focus on the statistics, not the original values directly from the population. So we will consider the sampling distribution of a statistic. So we will focus on the statistics. Statistics are the estimators. So we have this general behavior of sampling distribution. We will say the same size sample from the same population. So the same population. From the same population, we can get a lot of sample, right? Each time we randomly select someone. Let's say if each time we select 50 observations as our sample. So we can find a lot of samples and with the same size. So this is the bottom line. Same size and from same population. We will follow proportions, the sample proportions, normally distributed. Or the sample proportions tend to be normally distributed. And the mean of sample proportions is the same as the population mean. So that's the general properties. So first, the sample proportion follows a normal distribution. The second one, the mean of the sample proportions is just the population mean. Let's check this graph to help you understand what that means. It's kind of like tongue twister, right? So from the same population, we can get several samples. We can get infinity samples. Each sample has the same size. So for example, we have sample 1. Then for this sample, we can get the proportion. Let's say p hat 1. P hat 1, right? The second sample, we can have p hat 2. So if we have 100 samples, we will have 100 p hats, right? So we will see all the p hats follow a normal distribution. So I put this normal curve here. All the p hats follow the normal distribution. Again, how can we get p hat 1? We have a sample. Then we can use all the values in this sample to get what is this p hat. So that's called p hat 1. And if we have 100 samples, we can have 100 p hats. If we have infinity, we have infinity p hats. And all of the p hats tend to follow a normal distribution. That's the first property. And the second property, we know if this one follow a normal distribution, then the mean of this p hat is just the original mean for the population. The mean for the p hats is just the mean for the original population. So the same thing is if we can have lots of samples, each sample have a x bar, we can use all of the values to find the sample mean, right? If we have 100 samples, then we have 100 sample means, and all of the sample means follow a normal distribution. Also follow a normal distribution. And we will say all of the mean of all the sample means follow, not follow, it's just the population mean. Mean of all the x bars, mean of all the sample means is just the mu. It's just the mean of the population. But let's see this one. The same thing, we have lots of sample. Each sample we can get this variance, right? Each sample we have a variance. So s squared 1 for the sample 1, s squared 3 for the sample 3. If we have 100, we have 100 s. All the s squared do not follow a normal distribution. It's just follow a skewed distribution. So not like the proportion, not like the mean value. The variance of the sample do not follow normal distribution. So it's the sampling distribution is just the distribution of all the values of a statistic. It's not the distribution of the original data value. If we are talking about a sampling distribution, we are actually talking about the distribution of all the mean value, of all the sample mean, of all the sample proportion, of all the sample variance. We are talking about the values of statistics. We have lots of sample means. We have lots of sample proportions. We have lots of sample variance. Not talking about the value. Not talking about the x value. And again, the bottom line is same size and from the same population. Again, we restate the property of this distribution of p hat. We're talking about sampling distribution. This sampling distribution is just about the sample proportion, so we use this notation, p hat. If we're just talking about p, it's just the proportion. Okay, if with the hat, that means the sample proportion. If it's the p hat, again, p hat is the sample proportion. If it's just p, then it will be the population proportion. So we know same size, same population, then it's normally distributed. All the values of p hats are normally distributed. And the mean of all the p hats is just equal to p. So again, p without hat is about population. P hat is just about sample. So the first property of sample proportion is all the sample proportions follow a normal distribution. Then the second rule, the expected value. So another way called the mean value, right? The expected value, remember, is another way called mean value. The expected value of the sample proportion, we will say it's just the mean of the sample proportion. It's just, we have 100 p hats. We add them up, divided by 100. That's the mean of the p hats is equal to the p, the population proportion, is equal to the p. Let's see the example to help you well understand what we are talking about. Repeating the process, roll a die 5 times. So each each time we should roll a die 5 times and repeat this process lots of times. We want to find the proportion of odd numbers. So 5 times we have 5 numbers, right? Roll a die 5 times, we will get 5 numbers as our result. Then we try to get the proportion of odd numbers. We can only have 1, 3, 5. So we want to get the proportion of odd numbers. Then we want to know the behavior of all the sample proportions if this process continues indefinitely. So we can check this graph. Let's say, for example, we roll a die 5 times. This is our first sample. We record the result. We have, for example, we have 1, 2, 2, 4, 6, 5 numbers. Then we realize what is the proportion of odd number. If the sample one we got the result as 1, 2, 2, 4, 6, so we only have 1 odd number out of 5 numbers, right? So the proportion will be 0.2. So for example, the second sample, we got 1, 5, 2, 2, 2. So this time we realize we got 2 out of 5, 2 odd number out of 5 result. So the proportion will be 0.4. And we repeat this procedure lots of times. Each time we will get the proportion of the odd number. Then we record the number. And we have lots of proportions, sample proportions. We try to use the frequency histogram. Remember, we have the frequency histogram to record all of the proportions. Then we get this curve. The histogram will show us all the proportions, p-hats, follow a normal distribution. If we have repeated this procedure 10,000 times, then we use software to help us to draw the histogram. We will realize the curve is just a bell-shaped curve, right? So this one just tell you, follow the normal distribution. And we use a software to help us to find the mean of all these 10,000 p-hats. We will get the p is equal to 0.5. The mean is 0.5. Of course, the proportion of the odd number in population is also 0.5. Why it's 0.5? Because we know we have 3 odd numbers, 3 even numbers. So the odd number and the even number, they are equally likely. So the proportion of odd number in the whole population, it should be 0.5. And by using the software, we know the mean of all the sample proportion is also 0.5. So we just know this is our second property of sample proportions. So the second topic is about the sample distribution of x-bars, sample mean x-bars. So it's very similar to the proportion. We know from same population, same size, same population, always have this rule. And all the x-bars follow a normal distribution. And the mean of all the x-bars is just the mean of the population. So this is again normal distribution. Mean of the sample mean, or the expected value of all the sample means, is just the population mean. Again, the expected value is another way to call the mean value. Let's see the same example. But this time we want to find the mean of all these 5 numbers. We still roll a die 5 times, then record all the values. So 5 times, we have 5 numbers, right? Then we try to record the 5 numbers, and for each sample, we have 5 numbers. We add them together, divided by 5, we can find the mean for the sample. That's how we find the X bar. Right? So if we have 10,000 sample, we roll the die 5 times, and we do this process 10,000 times. So we will have 10,000 group of 5 numbers. Each group of 5 numbers, we will find a mean X bar. So we will have 10,000 X bars. We will talk about the behavior of all the X bars. So for example, for the first sample, we record several numbers, 3, 4, 2, 5, 6, something like that. Then divided by 5. For example, for the first 5 numbers, we get 3.4. And for the second 5 numbers, we get this. So each one is our sample mean X bar, right? Then we use the histogram to help us to work on the shape of the distribution. We realize it's still the normal distribution for all the X bars. For the X bars, we follow normal distribution. Again, we use software to help us work on all the mean value for this 10,000 X bars. We get it's just a 3.5. It's just a 3.5. And we know the population mean is also the 3.5. How can we get to this one? How can we get to this mu? Because we know 1, 2, 3, 4, 5, 6, 6 numbers are equally likely. So how can we get the mean value? We only need to add them up, right? We only need to add them up. 1 plus 2 plus 3 plus 4 plus 5 plus 6. So total we have 6 numbers. We will find it's just 3.5. This is how we get to the population mean, mu. Because each number is equally likely. So we can get to this mean. And if we use technology, we will find the mean of this curve, mean of this sample means is also equal to 3.5. So if the process is continued indefinitely, the mean, continued infinitely, the mean will be just the same thing. Let's talk about another one, the sample variance. The sample variance from the same population with the same sample size not follow a normal distribution. Let's check this one. So this is the formula. Let's check the formula. How can I put it correctly? Make sure you check your PowerPoint. I think if you print out your PowerPoint, you will get the correct formula. So again, if we're talking about the variance, then we do not have square root. If we're talking about the standard deviation, we will have the square root, right? These are the correct formula. So it's not shown correctly here. Let's talk about the behavior. So first of all, the distribution is no longer a normal distribution. The variance is not just like the proportion or the mean. It's not a normal distribution. It's a distribution skewed to the right. Remember the previous graph? It's not a bell-shaped curve. It's a curve skewed to the right. And the variance target the population variance, or we would say the expected value, the mean of all the variance is just the population variance. So the mean, or another way we say the expected value of all the S squared sample variance is equal to the sigma squared population variance. So the first rule is different, but the second rule for variance is just the same as the previous two statistics. Let's check this one. Roll a die 5 times. We have 5 numbers, right? Based on these 5 numbers in one sample, we can get what is the variance. We can get the S squared. Now we are talking about the behavior of the sampling distribution. So this time we have the first 5 numbers. Then we use these first 5 numbers to get the variance, the first variance. And I do the same thing for the 10,000 samples. Each sample we got 1 variance, x squared, right? Then I put them into a histogram, frequency histogram, by using the technology. Then we find this one is no longer bell-shaped. It's a curve skewed to the right. But based on the technology, we know the mean value of all the S squared is just the same as the population, sigma squared 2.9. So that means the first rule is just different from the previous two, proportion or mean, but the second property, they are just the same. Okay, the mean of all the sample variance is just the same as the population variance. But make sure you know this time the curve is not a bell-shaped curve. That's the only difference. So here, let's check the definition of estimator. Estimator is a statistic to estimate the parameter, population parameter. So it's just a measure to estimate the parameter. We call it estimator, and the estimator is a statistic. Let's see, what is unbiased estimator? Of course, we prefer the unbiased estimator. You know what is unbiased? So this estimate targets the value of the parameter. Targets the value of parameter, which means the mean value, the expected value of this statistic is equal to the parameter. So we only need to memorize 3 important unbiased estimator. These 3. We talk about the behavior of these 3 estimators, and we know the mean of all the p hats is just equal to p, and we know the mean of all the x bars is just equal to mu, and we know the mean of order S squared is equal to sigma squared. So these three are three important unbiased estimators. And about biased estimator, you only need to memorize this standard deviation, because this one is very similar to the S squared variance, but make sure you know the variance is unbiased, but the standard deviation is biased. So about the sampling method, we only need to know we prefer the sampling method with replacement. Remember, if the sampling method with replacement, which means each selection is independent to each other. With replacement means independent. But we know the rule, 5% rule. Remember, if the population is very large population but a small sample, then we will treat all the sampling as with replacement, even in fact they are without replacement. So this just tells you we prefer the sampling method with replacement because we want to make sure all the sample is independent to each other. So that's all for this section. So I know this section is very boring, but this one is just the foundation of next section, the central limit theorem. I would say this is the basic information of the next section. Next section, central limit theorem, will be the most important section in the whole chapter. But our midterm will just stop at this section, 6.3. We will test the central limit theorem after the midterm.